Hey, Andrew McLaren here. We're going to be talking about Gibbs free energy and this equation and how it relates to phase changes, like when something's freezing or melting or vaporizing or condensing. And so we're going to be talking about a lot of these terms that are in this equation and how they relate to those phase changes. And we're going to be trying to explain how to solve like a problem where you have to like work with values for these to maybe find the melting point, or just in general, conceptually what's going on with phase changes, like why you see the phase change at that temperature and why it's spontaneous above or below either freezing or melting. So we're going to look at that and do some math to help explain conceptually how this equation really relates to those phase changes. We're going to do that by looking at the main idea and just talking about this equation. And then we're going to do some simulations. And then we're going to compare the various types of phase changes, looking at the phase change and temperatures just above and below those phase changes. When we're talking about a phase change, you can think about this first part of the Gibbs free energy equation canceling out the second part right here, because we've got this first part there, the second part there. They kind of cancel each other out. But before we talk about the phase change, you really got to think about what these terms mean and just kind of define them. And then it will make sense why they cancel each other out at a phase change, right? Um, so this is how I've defined these terms. When I think of Gibbs free energy, I think that's work, or that's like what I associate with spontaneity. If something is spontaneous, you're going to have a negative value for a Gibbs free energy. So a negative is spontaneous. So if you have like negative 10 joules for the G value, then it's spontaneous. If it's positive 10 joules, then it's not spontaneous. It needs that much energy to go forward, plugged into the system to actually get it to go forward. Whereas the other one releases that amount of energy and it's like a ball rolling down the hill. Okay. So that's the first part, is that this is really an indicator of spontaneity. So when I see the G, I think spontaneity. That's the main word right there. This guy right here is what I'm thinking about when I'm thinking of G, or Gibbs free energy. When I'm thinking of the change in H, this is enthalpy. This has to do with therm, or things are thermal or having to do with heat. So this is having to do with that change in terms of heat. So if something is getting more energy, um, it's like a ball being rolled up a hill. That doesn't happen spontaneously. You need to plug in some heat to do that. And so you can see how when you have a positive number in here, it makes this a little bit more positive. It's like contributing a positive, so it's making it less spontaneous overall. It's opposite here is this is like a ball rolling down a hill. This is our exothermic if this is negative, right? And so that's our energy having to do with thermal. And then you have your temperature. This is, you can think of this as like the speed of the molecules, what they're moving at, and the entropy. And entropy is kind of a weird thing for people to define. But when I think of entropy, I think of the word options. Like if you have more entropy, there are more options. It's an indicator of the level of chaos. So you can imagine if there's a lot more places that you could hide, that's a more chaotic system. It's kind of harder to know where something's going to be. It's harder to make those predictions. So if there's more options, there's more entropy. So if there's more places or layouts for things to be arranged in, that's going to be an increase in that S value. So it's pretty also important to note that you can also look at the cell's voltage, if you're talking about the energy of a battery, and that's related to the Gibbs free energy. So how spontaneous something is going to correlate with its voltage. Just trying to link about what these things really are. So we've got like spontaneity, heat or energy, the speed things are moving at, and the change in the amount of options between the two sides. So that's the main equation here. When we're talking about like a phase change, the first part, the change in H, that part cancels out the T times the change in S. They're going to end up having opposite contributions to the change in G. So if this is like a minus right here, right? You're going to expect this whole term to end up being like it's being added, okay? And what ends up happening is that if you have like a minus in here, you're subtracting a minus, so it ends up adding, right? So they end up kind of canceling each other out. The first part and the second part of the term end up canceling each other out. As long as the change in H and the change in S are the same sign, they cancel each other out. Same thing if I had a positive number here and I had, let's do this as its colors. We've got our positive number there. You can see I've got a positive and I'm subtracting another positive, so they cancel out and you get a G of 0. So that's the main idea when we're talking about phase changes. The first part and the second part end up canceling each other out. And we're going to talk about next about conceptually what that really means. But it's important to keep that in mind, that essentially the two parts are fighting each other to determine if it's going to be spontaneous, like a negative number, or if it's going to be a positive, or not spontaneous for our Gibbs free energy. Because this is the same equation as we have right here. We've got that same equation. I've just kind of put in placeholders here. This is our like change in G. This is that change in H, T, and change in S, right? So you've got those different different parts of the Gibbs free energy equation and how they relate to each other. Now, it's also important to keep in mind there's a couple graphs that I like to think about when I'm thinking about my phase changes. And the first one is your Q, which is that heat, comparing it to the temperature. And it's really important to be thinking about this and how it relates to the Gibbs free energy, because they're super connected. You can also think a little bit about what's going on with the temperature and pressure. These graphs are good to have just some familiarity with. Like you've got like a constant pressure, and this is that boiling point and freezing point for water. Okay. I'm not going to spend a ton of time on these graphs, but I'm going to refer to parts of what's going on here. Also, water has a slightly different slope because um, ice and water, I think ice floats, but for most things, solids are more dense. So if you increase the pressure, it'll make more of the dense thing, right? So that's kind of like ice skates. When you skate on water, it turns it into a liquid water because it's increasing that pressure, turning it into a liquid. And then this is kind of like, okay, you're adding heat to a certain system, and then it starts, if we're talking about water, this is at that 0 degrees Celsius, and this is at 100 degrees Celsius, because something will freeze or melt at 0 degrees Celsius. And you've got some energy that you're adding, and then it stops changing the temperature, but it is increasing the amount of Q or heat in the system. And then as you add in more heat, now the liquid can get warmer, and then it's staying at constant temperature while it vaporizes, and then as a gas, it can get warmer. Now, it's important to note that these are constant temperatures at the phase change, because we're talking about constant temperatures in our equations as well. And this is in general how this stuff is all related. But if we're talking about like freezing, what you're saying is, and if you think about a liquid's moving a lot faster, and a solid's like pretty slow and still and compact. And so the liquid is a higher energy state. So we're going from a liquid to a solid. And this is something that I taught my students, like my middle school students. If you know your energy of solid, liquid, gas, then you know the change between the two, right? So if you just can visually think about the relative energies of those things, you know the change in H, or at least the sign, right? So if something is freezing, what's happening is that it's exothermic. And so there's you can think that this is kind of making the reaction more spontaneous, because it's releasing energy. It's like a ball rolling down a hill in that regard. So it's kind of making it more spontaneous here, but it's actually making it less spontaneous here, because you're decreasing the chaos in the system, because the liquid is a more chaotic system than the solid, which is all neat and orderly. So when you've decreased the chaos, it doesn't matter that you've released energy, because they're kind of canceling each other out. and you end up getting a phase change of 0. So when you're at just the right temperature, um, it's not spontaneous forward. It's actually gives free energy of 0. So it's kind of like balanced between the two sides. Um, if you change the temperature a little bit, it's going to either become a negative number or a positive number, indicating that, like, for example, freezing is now spontaneous or not spontaneous. And so if we're talking about the opposite process, we can talk about melting. That's going from a solid to a liquid. So that's a positive Q. And so you can see that this is kind of like, okay, a ball being rolled up a hill, that's not going to happen spontaneously. But it actually is also increasing our entropy, because the entropy, because the liquid is more chaotic than solid, there's more options, more places. And so you can think about it in that regard as making the Gibbs free energy more negative. So when this is a positive, and temperature always is a positive, that ends up making this contribute a negative number, making the overall thing more spontaneous. So if you can think about these two things as like, oh, this is making it less spontaneous, but this is making it more spontaneous. And at this temperature, they cancel out and give you 0. And vaporization and condensation are the same idea, but they've got different values of change in H and change in S. So you can imagine if you've changed the numbers that you're working with here and there, then you're going to need a different T to get to the Gibbs free energy of 0. So like the vaporization and condensation, they've got different values that essentially are going to balance out at a higher point. You can think about it like that in a sense. Also keep in mind that the values that we're using for like the Gibbs free energy, the enthalpy, and the entropy, these are all from standard conditions. They do change slightly when you change the temperature. So you may see variation of some of these values, especially when you go to like higher energy states. These things are going to vary a little bit, but we'll get close enough. But there will be more error the more we vary from those standard conditions. So our calculations, sometimes if you look at some of the numbers, they'll get you close, but not exact. And that's because these values do change slightly as you get away from standard conditions. But we usually indicate the standard conditions with that little circle right there. And that's what we're working with when we see those values in a table. Okay. So that's the overall idea. You're trying to cancel out essentially the first and second part of the Gibbs free energy equation, so that it's not spontaneous forward or backwards, but kind of perfectly balanced between the two. Okay. So I wanted to also demonstrate enthalpy and entropy in the simulations. It's a good way to visualize it. So we've got one from PhET and one from Concordia, really good simulations from both of them. So if you look at your states of matter, they've just got like a little cartoon of our various states of matter just to show you what they look like. So you can see the solid is a nice, neat structure most of the time. And then the liquid is more spread out. It's more chaotic system. And the gas is the most chaotic. If you just asked me visually which one looks chaotic, I'd be like, this one looks like a classroom of 6th graders. It looks like chaos, right? Honestly, it's all about the places that they can occupy, and these have more space that they can occupy. The solid can't occupy all the space at the top of the container. They've got less places they can go, and they're also kind of locked in place. Like this one can't get over there, really, or this one can't really get over there. Not as a solid because they're kind of locked in place with their neighbors. The liquid, more places they can go, so there's more chaos. So there's more entropy, right? So we can talk about the amount of entropy at these different things. You can also talk about the amount of energy. So if I have a solid right here and I add in some energy, I can make it a liquid eventually. I think that that's starting to turn into a liquid, yeah. So like if I'm adding an entropy, then it can make this a liquid. If we're thinking about our equation right here, what we're basically saying is like, oh, okay, well, I'm changing the temperature now. Is this going to give me a spontaneous process forward? Like that that melting process became spontaneous because as T changed, the Gibbs free energy turned into a negative number, indicating that it was a spontaneous process forward now, or we had enough energy to make it a spontaneous process forward. And so you can kind of keep on going. And I think that we'll make this into, yeah, a lot of this is starting to turn into gas. You can kind of see it going to the top of the container there. So yeah, it's working pretty well. We're getting our change in enthalpy, which is that heat which they added with the fire and whatnot. And the entropy is really where they are or where they can be in the system. I also really like this series of simulations from Concordia. They've got a number of good things that help you think about what's happening at the different phases, and that is good for you to think about the entropy and enthalpy. So if we're looking at like a gas, you can think about what's happening with the molecules. And I like this for tracing and showing the molecules and how they move. And then they do the same thing for like the liquid, and you can kind of see how that moves. And you can see that there's some movement here, but less movement than the last one for an individual molecule. Like it can move around, but not quite as well as a gas. Like there's less options or places for them to go to. But the solids, they're pretty much locked in place. There's very few options for them. They're interacting with their neighbors. They don't go anywhere, right? So this is a good way to show the entropy of the different phases. It also has some good things to help you think about why some things would maybe be a gas when other things are a liquid or a solid. And it has to do partially with their interactions. Like, water has some stronger interactions than like ethanol. And so like it's going to be a liquid where ethanol would be turning more into like a gas under the same conditions. So you can think about that's kind of why certain things will be spontaneous at lower or higher temperatures. It's because they're needing to break those interactions to get to the next stage. And stronger interactions need more energy to be broken. We can also look at what's going on with phase change and the energy in molecules. And so there's this pretty good one that shows you, okay, you had like a liquid and a solid, and then when they mix, their averages kind of, well, one gets more energy, one gets less until they're about the same, right? So this is a good way of thinking about what's going on with energy as well as that entropy. And they do have some other little simulations here where you can see what happens as you add energy to that state of mass or state of matter. And you can think of this in terms of our equation, right? That you're changing the temperature. And as you change the temperature, the amount that this affects the G is going to change, right? So you might be able to make it spontaneous if you increase the temperature enough for these like vaporization or whatever. So that's the main idea. And then this, I think the next one that's pretty good is the one on slide 9. This one also shows you like, okay, well, if I have the same substance and I change the temperature, what does it look like? And you can kind of see like the more chaotic system is the higher temperature, things are moving around more, right? But you can actually also see that the charge, it doesn't move around quite as much at a high temperature as something that was non-charged. These are flying around a lot more. These are flying around a little bit less, right? So you can think about that's kind of why certain things are going to be also interacting a little bit differently at the same temperature. So if we're talking about water, it freezes at 0 degrees Celsius. We know that. It's just a pretty common number that we're familiar with. So we're going to talk about that phase change. And so we have the change in H value for this process and the change in S value for this at standard conditions. So we're going to use those standard values, though it would vary slightly from those standard values. So if we're thinking about freezing, we're going from a liquid to a solid. So this is happening at 0 degrees Celsius for water, if we're talking about that process. Oh no, it's getting kind of slow on me. So we've got 0 degrees Celsius right here. And basically, you can also think about this as going from the liquid here to the solid, and we're at like standard pressure, so it's standard conditions. And so it's going from here to there. And so when it's doing that, it's like wanting to turn into the solid, right? So you can think about that as what's kind of going on conceptually. It's important to think through this stuff conceptually, because then that helps you kind of realize what's going on with these numbers and their values. So if we plug in these values, you can see that this is exothermic, but this is also creating less options, right? So this is kind of like, oh, this is making it spontaneous. This is making it non-spontaneous. If you're at just the right temperature, they should cancel each other out. And that's what happens. So if you see for this process, if we look at 0 degrees Celsius, this is actually supposed to be, I think it's 273.15. It's slightly different. You don't add exactly 273, you add 273.15, which can be somewhat important with these calculations. You can see if I calculate this out, if I multiply this number times that number, I get negative 6,000-ish. I'm subtracting that negative, and I have a negative, so they end up canceling each other out, right? Because this is like a giant plus sign. You can think of that in a sense when you've got you're subtracting a minus, it's like you're adding, right? So those parts kind of cancel out. We effectively have a Gibbs free energy of 0. And so we can say that at this point that it's not really a spontaneous reaction forward. Then you should ask yourself, and we'll go through some calculations like this, does water freeze at 10 degrees Celsius or negative 10 degrees Celsius? And just kind of conceptually check that. And so I know that water freezes, so this is spontaneous, and this is not spontaneous. And so I'm just kind of gonna check that with our actual math now. So if we go ahead and plug in these values, we should be able to do that. Sorry, just give me a second. So it's virtually the same calculation. It's just slightly different because now instead of having the temperature at 273 and 15, it's a slightly different temperature. So we have the same here, same there. This has changed, which will result in that changing as well. So instead of 273.15, this is going to be 283.15. And so if we do that, we get, what is this? 283.15. I'll make that also red just to be good with our color coordination. And then if we get our calculator out, we can take our 283.15 times that by our 22. And we've got 6,229.3. And this is, we're kind of adding this because it's subtracting a minus, right? And then this is kilojoules. These were joules. And so you can see that's why in the last problem that we had to write this from kilojoules as joules, and I had a little conversion factor there as well. So if we convert this into joules, we already did that. It was the this number right here. So we got the same number, but now we end up having a non-spontaneous value because we're having a positive sum. Like if you add up those two numbers, you get this, let's do minus, right? And so you've got 219.3 joules per meter, or per mole. And then our last sig fig on this one was in the tens place. So our last sig fig is in the tens place here. So we can estimate this as 220 joules per mole. So yeah, you can see that this is not spontaneous. So that kind of matches that, right? The fact that it was a positive. Okay. And then we can do this exact same calculation, but slightly different numbers. And we're gonna be at a different temperature, and it should result in a different calculated value. So you can probably see at this point how this works. And I'm just gonna be doing calculations from here on out, essentially. So we've got the 263.15. And if we multiply that by the 22, let's see what we get. So we got 263.15. And yeah, like I said earlier, these numbers are not perfect because we're in non-standard temperatures, right? So these values aren't exactly accurate, I mean, technically, but they're close enough. Okay, so we've combined those two parts, that red and that blue, and you can see if we were to sum those up, we end up getting a negative 220.7 joules per mole, and we can say that this is going to estimate that place value. So this is at negative 220 joules per mole. And that matches what we said earlier. This is a negative value, and we know that Gibbs free energy, when it's negative, is spontaneous. So it's pretty nice when it works out like this. And you can actually do this with another compound as well, and you'll get slightly different values. I ended up cutting that one out in the long run, and just focusing on water just to save some time, though. Okay. So when we're talking about melting, it's the opposite of freezing. So if you think about that, you're changing the signs on all the numbers. It's the opposites, right? And so the Gibbs free energy should also be changing signs, but it's actually the same numbers that we were doing in the last section. It's just now positives are negative, besides temperature, because temperature is always positive. It kind of conceptually wouldn't make sense to flip that one. But if you look here, you can see the change in H is positive, the change in S is positive. We're going the different direction on the graph. And so we're going from the liquid to the solid to the liquid. So it's an increase in the entropy. So we know that this is a positive sign because it's going up, right? This is a increase in that H. So like how we looked at this last time we were looking at, sorry, I wanted to just refer back to one of these graphs. Yeah. So it's like, you know how we were saying the melting is going from the solid to liquid, which is opposite of that freezing in terms of energy. That was what I was trying to refer to. Okay. And then melting, you can think of this as going from the liquid to the solid. So that's kind of where it is on this graph as well. And you can think about it as making there be more options in the liquid as well. So there's an increase in options or places that it can go to when you go to the liquid because it's more spacious, right? So that's why that would be positive here. If we look and do the math, these are literally just positives where we had negatives last time on the equation. So last time we were working with a negative here and a negative here. Now we're working with positives. And if you do that at 0 degrees Celsius or 273 degrees Kelvin, these cancel out. So it's not spontaneous forward or backwards, the process of melting. It's perfectly balanced between the two. But what happens that's kind of interesting is when we're talking about the melting here, we can think like, well, does water melt at 10 degrees or negative 10 degrees Celsius? And this is gonna be, yeah, this should be spontaneous, and this should be not spontaneous. I believe that's opposite from the last one. Yeah, they've kind of like flipped. At 10 degrees, freezing's not spontaneous, but melting is, which kind of makes sense. If water is above its freezing point, it should melt, it should turn into the liquid, right? So if we think about this, we can then plug in our numbers, and suppose that should be 273.15, right? And then this is going to be, instead of that 273, the temperature that we're at now is 283. So if we get that, 283.15, this is actually the same multiplication that we did on the last section, right? It's just we don't have a negative on this one. So when you multiply these two, you get the 6229.3, I believe. Yep, joules per mole. And that, in this case, it looks like is negative, and that cancels out the positive here, which is great. So we've got like a 6010, because remember this, we have to turn into joules. And then we've got that as joules already, and then we can get that, and we get the whatchamacallit. So it's literally just like the opposite sign of what we did last time. So this is 219.3 joules per mole. It looks like this should be negative. Let's just double check this. Okay, and this does make sense because this is negative here, which is indicating that it's spontaneous. And so water should be, we're talking about melting, it should be spontaneous when we're above that melting point, right? And so we can see with our calculations how when you have a positive number here and a positive number there, the two parts kind of cancel out if you're at the melting point, but if you're above and below it, it's going to be either slightly spontaneous or not, depending if you're talking about the freezing or the melting. And so you can do the same thing for our last part here, and it's just the opposite sign. So I'm just going to plug those in. And so now this is our positive, that's our positive. And so this no longer is negative, but this does become negative. The whole thing on this side does become negative. And then this is a positive value. And so you can say that. Oh, and I should probably estimate this to my sig figs right here. So it's that 220. Okay. And so that's the main idea here. If one's spontaneous, the opposite process should not be spontaneous. It should be the opposite. It needs that much energy to go through the process, right? And so when you're talking about the opposite process, you're just flipping the signs, but it's the same sort of math, okay? So that's melting, and that's kind of the idea with why this is non-spontaneous. It helps me to just kind of think through what these things mean at these different points, just to give a couple examples. We'll do the same thing with vaporization and condensation, though you may be getting the big idea and kind of know what I'm going to show you there. It's good to see briefly the other numbers. All right, let's talk about vaporization. It's the same sort of idea, but you can see now we've got different H and S values. So when we're talking about the different amount of entropy or enthalpy, we're comparing the liquid to the gas now. So the amount of difference between them is going to be significantly different. So there was an amount of difference between the solid to liquid for like H or S or whatever. And then there's also our gas, which is much higher in terms of its energy state and the amount of options that it has. And so you're going to be seeing much higher values for both of these things, right? So if we have this table, we're looking at vaporization. So if we're talking about water, this happens at 100 degrees Celsius, which is just a nice, neat little number that we typically talk about. It's also, I think, 212 or 214 degrees Fahrenheit. So we know water boils at that temperature. So if we're at that temperature, we actually have a little bit of liquid and gas, and there's both vaporization and condensation happening equally at that point. Um, if you're higher, you should have more gas. If you're lower, you should have more liquid, so on and so forth, right? Kind of like what we did with the last part with the liquids and the solids. So now if we're vaporizing, we're going from the liquid to the gas. We're going to be going to that state that has a positive in terms of that energy change and also the amount of options. So they should be kind of canceling each other out in the formula. Vaporization is like you're increasing the energy, so this is very much like that melting process. They're analogous to each other. So if we plug in these numbers and you calculate this, you get something that's about 0. Again, we're getting kind of away from our standard temperature and pressures if we're not at exactly room temperature, so this number isn't perfect. There's some error in here. But you can see that it was not spontaneous because it's, a ball getting rolled up the hill in terms of its energy. But it is actually making more chaos. So it is kind of spontaneous in that part. So this is negative. It contributes negatively, right? And so if we consider these two, they basically cancel each other out, and we've got no spontaneity. It's not spontaneous or not. It's just kind of like nicely balanced between the two sides. Now we can take that and we can consider above and below that temperature, right? So if we're at a slightly higher temperature, you can imagine what's going to happen. This number will change, right? Which will change these numbers as well. So let's go ahead and see what we get. We got 383.15 times 108.96. Okay, so we got 417.48. And we could keep on writing it, but I very much doubt that we're going to have that many sig figs. So we kind of just cut off there. And there was a decimal point and some other numbers. This I know is limiting right there. So our final answer is going to get limited in the hundreds place anyways. So it's just kind of like, why go way further? Right? Okay, so we've got that number and subtract 40700. And we get 1048 joules per mole. And then if we round that to the hundreds place, it's actually gonna be 1000 joules. And it looks like to me like this should be negative, right? I'm just gonna double check that that is kind of what's going on. We're above this, and so this should be spontaneous. Okay, because we're talking about vaporization. So if we're at a higher temperature, we're gonna be like gas, it's gonna vaporized, right? So that process of vaporization is spontaneous and it moves forward if you're above that temperature, right? Then you can do the same thing, but a different temperature. So same sort of calculation, but instead of at, come on, there we go. Wasn't letting me click. 363. So yeah, I just did like some easy numbers just so you can see that we're just a little bit above and below that boiling point. So if we got 363.15 times 108.96. Okay, it looks like we got 39,563. Let's do that here. Yeah, you could keep on going, but this is gonna get limited in that hundreds place like we did last time. Let's see. I think it ends up kind of positive this time, yeah, because it should be a positive minus, yeah. So we should have a positive value. And then let's see. This is just the difference between the two. It should be a positive 1,131. And I mean, you could have just done the numbers a little bit differently, right? You could have done the 40700 minus the 9563 should give you the same number. Wait, what? Something weird happened there. Let me just double check that. There's a small calculator error. I just plugged in the wrong number. So we're rounding to the hundreds place here, right? That didn't really affect things. So we end up having the 1,100 joules per mole. And so that is not spontaneous, which kind of matches what we're seeing right here. So, yep, this coming out with a positive value makes sense because we're below that boiling point. So we're not going to be vaporizing into a gas here. That's not going to happen unless you add energy, right? Okay. Okay, the last one is condensation. This is when we have the change in H, the amount of energy. It's going down because we're starting a gas going to that liquid. You can see that I've got that shown over here as well. You can also kind of think about it as going from the gas to the liquid, right? Because the gas is up here and the liquid's down there in terms of heat. So we have to lose heat during this transition, but we're also losing options. So yep, this is making it likely to be spontaneous, but this is making it likely to be not spontaneous. But the right temperature, they cancel each other out perfectly, right? And that's our condensation point or vaporization point, also sometimes called the boiling point, right? It's all that 100 degrees Celsius for water. We're still at 100 degrees Celsius for water when we're talking about that boiling point for water. So if we look at the Gibbs free energy at that boiling point, the Gibbs free energy should be 0. So these are kind of like balanced. It's not spontaneous forward or backwards. It's really nicely balanced. So if we're talking about condensation, this should be not spontaneous. And this should be spontaneous. Because if you're below that boiling point, things should be condensing down into the liquid. If you're above it, it's not really going to happen spontaneously. So kind of like what we did on the other ones, the signs are going to be switched, but it's actually the same, change in H and change in S. It's just we're going down as opposed to up last time. So we've got negative values in here, and you can see that is what I did above, and a negative value in here as well. And let's see what we get when we do that, because it should give us something we can work with. So we got our, I think, actually, what am I doing? This is the same math as last time, but different signs. Isn't that what happened on the other one? Yeah, it is. Because if I did this times that, I would get negative that number. And I believe this becomes a positive because you got kind of a negative number, and then you're going to the other negative number. This is like final and initial. You can think of it as being like very low going to slightly higher in a sense. So yeah, this is a positive change. Okay, so this is not spontaneous. But if we look at the same thing happening, but at a different temperature, oh, where is it? There we go. Okay. So now we're talking about the 365, and we do have our negatives, right? Because we're going down in terms of energy and chaos, or options, measurement of chaos. I know it's kind of awesome that you can measure chaos, isn't it? I believe this ends up being a negative number, and that ends up being a negative as well. And so that matches this being spontaneous. Yes, that is what I believe ends up happening right there. Yep, because you're adding something that's not going to bring it quite up to zero. It'll still be a negative. Okay, yeah. So that's in general how you do these calculations, as well as how you think through phase changes and Gibbs free energy. Long story short, it's either spontaneous or not, and that depends on if you're above or below that temperature that the phase change happens at, like that boiling point or that freezing point. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about, and remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia, and if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.